Hello students, this is part 2 of our lesson on the extraordinary and important properties of water, and we're still covering pages 32 to 37 in the Campbell Biology in Focus textbook. We've already covered 2 of the 4 properties of water, and we've still got 2 left to talk about. And I just wanted to remind you, for each property of water, you need to be able to do 3 things. You need to be able to state the name of the property, describe and explain the property, including examples and any important vocabulary terms that I use. And then thirdly, you need to be able to state the biological significance of the property. Why does this particular property of water matter to living things? How does it help living things? That's what we mean by biological significance. So the third property of water is this. Water is resistant to change in temperature. In other words, especially a large body of water tends to stay the same temperature. Water is very slow to heat up compared to other chemical compounds, and water is very slow to cool down compared to other substances which lose their heat much more rapidly. So water tends to stay at a relatively constant temperature, especially a large body of water. Obviously, the larger the body of water, the more likely we are to really see this property. But another way to say the same thing is to say that water has a high specific heat value. And this is kind of a chemistry term. I've given you the definition here. Specific heat of any substance, not just water, but the specific heat of any substance is the amount of heat energy required to raise the temperature of 1 gram of that substance. Now that's a tiny amount. 1 degree Celsius. So if you have 1 gram of water, 1 gram of alcohol, 1 gram of sand, 1 gram of meatloaf, whatever it is, the specific heat is the amount of heat energy required to raise the temperature by 1 degree Celsius. Now, I'm going to give you some specific heat values of about 3 or 4 different substances. I don't expect you to memorize these numbers. I'm giving them to you so you have something to compare with water. So the specific heat of sand is 0.19 calories per gram per degree Celsius. Now, the first thing you're probably thinking is, what are calories? Calories is something we normally associate with food. You don't eat sand. And I know that sounds strange, but technically in a chemistry setting, in the context of chemistry, calorie is a measure of heat energy. So that's kind of weird because we don't normally think of it that way, but that's really what it means. So it takes 0.19 calories of heat to raise 1 gram of sand 1 degree Celsius. That's what that means. Now that doesn't mean much to you unless you compare it to something else. So how about the air in this room, the air in your house, or the air outside today? It's a little harder to heat up air. It takes a little more energy. It takes a little more heat to raise the temperature of air. Air has a specific heat of 0.24 calories per gram per degree Celsius. Alcohol, like isopropyl alcohol that you would buy at a drugstore, has a specific heat of 0.58. So just to kind of put this in context, the specific heat of alcohol is roughly 3 times greater than sand. What does that mean? It means alcohol is going to heat up slower than sand. the lower the specific heat, the faster the substance will heat up. Now, again, I don't expect you to memorize these numbers, but look at what happens when we compare these values with the specific heat of water. Water has an extraordinarily high specific heat. It has a specific heat of 1. And it doesn't sound all that high, but look, the specific heat of water is over 5 times greater than sand. It's about 4 times greater than the specific heat of air. And it's almost twice the specific heat of alcohol. What does that mean? It means if you had a beaker of alcohol and you put it on a hot plate, a burner, and you have a beaker of water, same amount in each beaker, and you turn them on the same heat source, which one is going to boil faster? The alcohol is going to boil about twice as fast. It's going to take twice as long to heat up that water. Water has an extraordinarily high specific heat. Now, I'll give you an example of this that even though you might have never heard of specific heat, if you've ever been to the beach in early summer, like right after school gets out, early June, you have experienced this phenomenon. Let's say you go to the beach on a June day, middle of the day, it's hot, it's 90-degree air temperature, and you kick off your flip-flops and your bare feet touch the dry sand on that beach, and you instantly notice that sand temperature is much hotter than the air temperature. The sand heated up a lot faster than the air did. And so the sand might be 150 degrees. It scorches the bottom of your feet. The air temperature is a much cooler 90. And when you decide you need to cool off, you go run and you jump in the ocean. And as soon as you hit that water in early June, you notice, whoa, it is cold. This water, which had the same sun shining on it as the sand, the water is much, much, much cooler than the sand and much cooler than the air. And the reason is sand has a low specific heat, air has a slightly higher specific heat, so it heats up a little slower. Sand heats up really fast. Water heats up really slow because it has a very, very high specific heat. Now, the reason water heats up slowly and the reason it takes so much energy to boil water, so much heat to boil water, is because of the hydrogen bonds in between the water molecules, causing these water molecules to cling to each other. When you heat up liquid water, you put water in a pot, you put it on the stove, and you turn up the heat. In order to boil that water, you're having to convert it from a liquid into a gas. So as you heat up the water molecules, the amount of kinetic energy, that means the energy of the water molecules moving around in the pot, that energy increases. But in order to turn the water into steam, these molecules have to have enough kinetic energy to literally leap out of the pot from a liquid state into a gas state and start floating around the room. That takes a lot of energy. And see, when you heat up water, the molecules don't want to leave the pot because they are all connected and held together by these hydrogen bonds. So in order to raise the temperature of water, in order to allow those water molecules to turn into a gas and leave the pot and leap out into the air, first the hydrogen bonds have to break. So it takes a lot of heat to break these hydrogen bonds, and only after the hydrogen bonds begin to break will the temperature increase, and then eventually there's enough kinetic energy that will allow some of these water molecules to start jumping out into a gas state. So we say there's a lot of different ways to kind of say the same thing here. We say water is resistant to change in temperature. Another way to say the same thing, water has a very high specific heat. Another thing we can say is that water has an extraordinarily high boiling point because it takes a great deal of heat energy to break the hydrogen bonds. That has to happen before the water will actually boil. Now, what is the biological significance of this? Yes, it makes cooking slower. It takes a long time to boil water in the kitchen, but that's not biological. Why does this matter to living things? The fact that water can hold on to heat so well helps organisms, especially warm-blooded mammals like you and I, to maintain homeostasis. That means it helps us maintain a stable internal temperature. All the water in your body, the water inside your cells, helps your body temperature maintain that stable 98.6 most of the time. If you are an animal or a plant that lives in water, like if you are an aquatic organism, a fish, for example, living in the ocean or living in a lake, all that water around you will protect you from radical changes in temperature. So those of us like you and me who live on dry land, we're surrounded by air, we have to be able to adapt and respond to rapid temperature changes. In the fall, you might have a day where there's a high of 85 degrees, and the very next day it might be a high of 50. So air temperature changes radically overnight sometimes. But aquatic ecosystems like oceans and large lakes hardly change temperature at all. They never change more than maybe 1 or 2 degrees in an overnight period. And finally, all the water that we have on planet Earth, and we do have something like, 78% of the Earth's surface is covered in water, all of that water stabilizes the global climate. If you were to go to a planet like Mars, which is approximately the same distance from the sun as the Earth, it's a little bit further away from the sun, but not much. But it has no water. There's no liquid water on Mars. The daytime temperature on Mars is like 400 degrees hotter than the nighttime temperature. It fluctuates that much in a 12-hour period. 400 degrees. That's huge. But on Earth, because we have so much liquid water, the daily fluctuations in temperature is not nearly as great as it would be without that water. Okay, so before we go to the fourth and final property, let's just have a quick review of the 3 properties of water we have discussed thus far. The first property of water was that water molecules are attracted to each other and to other polar compounds. Second property of water, water is a very effective solvent. Remember, specifically, water can dissolve anything that's hydrophilic. Water is unable to dissolve things that are hydrophobic. And then the third property of water that we discussed is that water molecules are resistant to change in temperature. And now our fourth and final property of water. Remember, I'm discussing these in random order. It does not matter which order you list the properties, because no property is any more important than any other. But the fourth extraordinary, unusual property of water is that ice, the solid form of water, is less dense than the liquid form. Ice is less dense than liquid water. And you might think, well, duh, everybody knows ice floats. If I put an ice cube in a glass of water, I know it floats to the top. That's not a big deal. But that really is unusual. Any other liquid substance, if you freeze it, it gets more dense and sinks. Like the solid form of almost every substance on Earth is more dense than the liquid form, but with water, it's the opposite. The solid form is less dense. And the reason this is so, like all the other properties of water, is because of the slight positive charge that every water molecule has on both of its hydrogen atoms, and the slight negative charge that water has on oxygen. Because if you look at this picture over here, this is liquid water. Notice when we say that liquid water has high density, that means the water molecules are pretty close together. They're tightly packed. Well, as water cools off, if you take liquid water and you put it in a glass and you put that in the freezer, it doesn't instantly turn to ice. It takes some time. But as that liquid water gets colder and colder and colder, the water molecules get closer together, closer together, closer together. So the colder the water gets, the more dense it gets. The water molecules actually get closer together as the water gets colder, until you reach a really cold temperature of 4 degrees Celsius. 4 degrees Celsius is sort of the magic number when the water molecules are as close together as they can physically get. And as the water gets colder than that, 3 degrees, 2 degrees, 1 degree Celsius, of course 0 is where it starts to turn to ice. As the water gets colder than 4 degrees, what happens is this little hydrogen, you see where can everybody see my laser pointer? Look right where I'm pointing here. This little hydrogen, which is positive, gets too close to this little hydrogen, which is positive. And this oxygen, which is negative, gets too close to this oxygen, which is negative. Now remember, opposite charges attract. But what happens when like charges get close to each other? What if a positive charge gets really close to another positive charge? They don't like each other. They repel. So when water gets really cold, liquid water, we're still talking about liquid water, when it gets really cold, 3 degrees, 2 degrees, 1 degree, those like charges start pushing back. They repel each other. And that causes the water molecules to space out the way we see them in this picture. And when it becomes a solid, when it actually becomes a solid block of ice, the hydrogen bonds in between the water molecules prevent them from coming back together. So they kind of are locked in that spaced out, low density structure. Okay. Now I'm going to kind of walk you through that step by step, but you know, even if you didn't quite catch all of that, you can tell from this picture that the liquid water is high density, but the ice is low density. There's a lot of empty space in between the water molecules in the solid form, and that's why ice has a lower density, and that's why the ice floats. So let's kind of go through this step by step. As liquid water cools, this is talking about my glass of water, room temperature, I put it in the freezer and I close the door. The water molecules get colder. And as they get colder, they lose what we call kinetic energy. Kinetic energy is kind of like the vibrations, the slight movements, the vibrating water molecules. The more kinetic energy they have, the more they vibrate. But as they get colder, they lose kinetic energy, and they're not vibrating as much, and the attraction, the hydrogen bonding between the water molecules pulls them closer and closer and closer together. So what happens is, as water gets cold, the density increases initially. At 4 degrees Celsius, the water molecules get as close together as they will ever get. That's the maximum density of water. It happens at 4 degrees Celsius. Water is still liquid at that point, and we still have our glass of water in the freezer, so it's still getting colder, so it's going to get down to 3 degrees, 2 degrees, 1 degree. Once we get below 4, the like charges, the positives and the positives, and also the negatives and the negatives, they repel each other. So the oxygen atoms on all the water molecules try to get as far away from each other as they can, and the hydrogens are repelled by the other hydrogens. That causes the water molecules to push back, to push away from one another, which causes the density to do what? It causes the density to decrease, right? If you space out molecules, they become less dense. At 0 degrees Celsius, that's when we go from liquid to solid. The hydrogen bonds lock the molecules in place, resulting in space between the water molecules. And you can see that very clearly in this picture. There's the empty space in between the water molecules. What created that empty space? It was the repelling force of like charges. Okay, now why does it matter that ice is less dense than liquid water, other than the fact that it makes my ice cube float in my ice water? Okay, the biological significance is it prevents lakes and ponds from freezing solid in cold climates. So if there's a lake in northern Canada where it gets really cold in the winter, the top of that lake will freeze as the air temperature makes contact with the surface of the lake. The top layer of water freezes. If water behaved like most substances, that ice would sink to the bottom. And then another layer of ice would form at the top and it would sink. And another layer would form at the top and it would sink. And pretty soon that entire lake, from top to bottom, would be a block of ice. All the fish would die, all the aquatic plants would die, all the microorganisms in that lake would literally die every winter. It would wipe out that ecosystem. Of course, it doesn't happen, because when ice forms at the top of a lake, it floats and it does not sink, and the liquid water underneath allows the fish and the organisms to survive. Having floating chunks of ice also provides animal habitats in polar biomes. So you see that penguins and polar bears depend upon these floating chunks of ice as part of their hunting territory, their mating territory. It's a very important part of their ecosystem. All right. So I have a video that kind of sums this up. It's called Liquid Awesome. It's from a series of videos called Crash Course Biology, and I will see if I can post that link for you. After you watch this lesson, you can watch that Liquid Awesome video review, and it kind of ties all of this together. Okay, so remember our 4 properties of water. Water molecules are attracted to each other and to other polar molecules. Water is an effective solvent. Water is resistant to change in temperature. And finally, solid water, ice, is less dense than liquid water. For each one of those properties, we described it, we talked about it in detail, and then we talked about the biological significance for each property. I have one more final thought. I'm just going to share a very quick little introduction to acids and bases, or the pH scale. I am not going to do a lot with this. I'm not even going to worry you really with the math part of this, because the math of pH does get confusing. but I do want to introduce this to you because a little bit of this will come up later in the unit. So when you talk about the pH scale, and this does relate to our discussion of water, because acids and bases are really just types of solutions where there's something that's been dissolved in water that affects the pH of the water. So what the heck does that even mean? pH literally means power of hydrogen. The pH of any substance is, now this is crazy, it's the negative log of hydrogen ion, this is hydrogen with a positive charge, hydrogen ion concentration. pH is the negative log of hydrogen ion concentration. Well, what does that mean? Well, you don't have to worry too much about what that means, except you need to know this, that the higher the concentration of hydrogen ion in a solution, the lower the pH. It's an inverse scale. So the lower the concentration of hydrogen ion, the higher the pH. Wow, that makes no sense whatsoever. I think it'll make a little bit more sense in just a moment. The other point that I want to make here without getting really into the math, because I know people's eyes just glaze over when you start talking about taking the negative log of a number. What the heck does that even mean? For now, suffice it to say that the pH of water is 7. That is considered to be a perfectly neutral pH. Okay. If we add acid to that water, notice the pH level is going to drop. When you add acid to water, you are increasing the concentration of hydrogen ion, which causes the pH to be lower. Remember, the pH of water was 7. The pH of a really strong acid would be 1. It's a higher concentration of hydrogen ion, but it's a lower pH. On the other hand, if we take plain water and we add a base, like this is called sodium hydroxide, it's a strong base, that will lower the concentration of hydrogen ions, but it makes the pH go up. It's a higher pH, 14 is higher than 7, but it's a lower concentration of hydrogen ion. I know it's weird, it doesn't make sense, but really, what do you need to know about pH? What is Mr. Cavaness going to expect you to know for a quiz or a test sometime about pH? Just a few things. Let me go through them. Here's the pH scale. It goes from 0 to 14. Right in the middle is a pH of 7. Halfway between 0 and 14. 7 is the pH of pure water. It is not an acid, it is not a base, it is neutral. pH of 7 is neutral. Any number below that, pH of 6, 5, 4, 3, 2, 1, 0, anything below 7 is an acid. And the lower you go, the more acidic it is. A pH of 0 is an extremely strong acid, like battery acid that could burn your face off if your car battery explodes in your face. It'd be terrible. Compared to, say, urine, which has a pH of 6, and it's just barely even an acid. It's a very weak acid. The lower the number, the higher the acidity. Or another way to say the same thing, the lower the pH, the higher the concentration of hydrogen ion. On the other hand, if we go above pH of 7, 8, 9, 10, all the way to 14, anything above 7 is the opposite of an acid. It's called a base. The higher the pH, the stronger the base. So that's not hard to remember. I know the math, all that negative log stuff is kind of confusing, But really, you just got a few basic facts. You don't have to memorize all these examples. Don't stress about that. But just know this. pH of 7 is neutral, neither acid nor base. Water is one of the few substances on Earth that has exactly a pH of 7. Anything with a pH below 7 is an acid. Anything with a pH above 7 is a base. And the final point that I want to make here on this pH scale is every time you go one whole number down or up the scale, like if I go from 6 to 7 or 7 to 8, or if I go from 14 to 13, if I make a whole number change on the scale, that represents a 10-fold change in hydrogen ion concentration. Do what? What does that mean? Here's what it means. Let's compare urine with a pH of 6 to tomato juice, which has a pH of 4. That's a 2 whole number difference, right? 6 to 4. So if I said to you, how many times greater is the hydrogen ion concentration of tomato juice compared to urine, looking at this scale? Well, from 6 to 5 would be 10 times greater. From 5 to 4 is 10 times greater. So if I go from 6 to 4, that's 10 times 10. It's 100 times greater. Every time you go a whole number, it's 10 times, 100 times, 1,000 times, 10,000. You multiply by 10. So let's do an extreme example. Urine compared to battery acid. How much more acidic is battery acid? How many times greater is the hydrogen ion concentration of battery acid compared to urine? Well, let's see if we can do the math. It would be 6 to 5 would be 10, times 10 is 100, times 10 is 1,000, times 10 is 10,000, times 10 is 100,000. So 100,000 times 10 to get us here would be 1,000,000. So battery acid is 1,000,000 times more acidic than urine. It has a hydrogen ion concentration that's 1,000,000 times greater than the urine. I think I did that math right. Let's see, 10 times 10 is 100, times 10 is 1,000, 10,000, 100,000, 1,000,000. Yeah, I think I did that right. Okay, so you get the idea. Okay, and then the last point I want to make about pH is the concept known as buffers. Buffers are solutions, chemical compounds, that resist changes in pH. A buffer is any chemical that helps keep the pH stable, keep it from changing a whole lot. And the only reason I mention this really in biology is because in a living organism, like let's take humans for example, you have many, many, many thousands of different enzymes. These are proteins in your blood, proteins in your cells that regulate the chemical reactions in your body. And those enzymes that are essential for you to live are highly sensitive to changes in pH. Normal pH of human blood is somewhere between 7.35 and 7.45. So look at that on the pH scale. It's slightly above 7. So it's slightly on the base side. So we would say that normal blood is slightly basic. It has a very narrow range of pH. And all the enzymes in your body are able to function within that range of pH. The only exception to that really would be like in your stomach, where you have stomach acid and the pH is much lower. So stomach enzymes operate at a much lower pH, but most of your body has to keep the pH between these two extremes. So your bloodstream has two different types of buffers that help keep the pH stable. The first one is called...
Brittany Sanborn, please come to the front.
The first buffer that I want to mention is called carbonic acid. This is the formula for carbonic acid. It's a very, very weak acid. Its job is to lower the pH of blood to keep it below 7.45. So if you have too much acid in your blood, carbonic acid, if your blood is not acidic enough, or if the pH gets too high, carbonic acid will bring it back down below 7.45. Bicarbonate anion, which is usually just called bicarbonate, does the opposite. It raises the pH of your blood to keep it above 7.35. So you have a way of maintaining homeostasis. If your blood gets too acidic, bicarbonate will raise the pH of your blood. If your blood is too basic, if it has a high pH, carbonic acid will lower that back down to keep the pH of your blood in between these two extremes. I know that's probably about as clear as mud. I didn't really go into a lot of detail on buffers. I just wanted to mention that concept so that next time you hear it, you can honestly say, I've heard that before. I remember a little bit about buffers. And I'm just going to leave it there. That's the end of our lesson on properties of water and a little quick introduction to the pH scale. Be ready for a quiz soon. Have a great day.